Hi, so today we want to tackle the problem of this system, which is commonly referred to as a coaxial cable. Now, coaxial refers to two axes. It mainly refers to the fact that in the system we have a wire in the middle where current is coming out, but there's also a larger shell in a sense where current is going back in, two axes. And we want to find the magnetic field at the center when we have different regions of consideration. For example, the first part is going to be the magnetic field as a consequence of this wire. The second region will be in the region in between the two, and then the third is going to be in this section right here, and the final is going to be outside this apparatus. Now I'll tell you, the second one and the fourth one will be the easiest, but these two will require a little more consideration. I will start from the inside out. This problem will be made slightly simpler by taking into account Ampere's law. What is Ampere's law? Ampere's law is that the integral of B dot dl is equal to mu naught times the current enclosed. Now the current enclosed can get a little bit tricky, and so I will rewrite this as mu naught, the integral of the current density enclosed, dot the area. Now this is going to be the part that makes finding the magnetic fields the most trickiest. In honesty, this will always be the same, but let's tackle this one quickly. Now the current density is defined as the current over the area. In this very specific case, the current is just I, and the area is going to be off this circle. That's just pi a squared. And I still have my differential area that I need to integrate over. Note, these two are not the same, so I will move that out. This is integrating the area of our Amperian loop. And so let me draw that now. Our Amperian loop is some distance r away from the center. And so the area of this is not necessarily going to be the same as the total area. This area is going to be, well, it's a circle, right? So we know the area for circle. Mu naught I over pi a squared. That's just pi r squared. But nicely, the pi's cancel out, and I'm left with mu naught I a squared times r squared. We still have the left side of our equation to solve, though. So this side is going to be equal to b times the length of the Amperian loop. And we can consider the same thing. That's just 2 pi r, the circumference of a circle. Now, there's an equivalence between these, so we can finally say that the magnetic field B is equal to mu naught I over a squared r squared divided by this quantity right here, 2 pi r. Now I can cancel 1 r, and I'm left with mu naught I over 2 pi a squared r. Alright, so now we've figured out this one, we just have to continue going down the drain. So, when r is less than b but greater than a, let me draw that Amperian loop. So that looks more like this over here. But the nice thing is there's only one current that's enclosed. It's just mu naught integral j dot dA, but it's the entire current. So we will denote that as just mu naught I. That's nice, and this left side is going to be exactly the same, b 2 pi r, as was last time. So I can just rearrange, and I find my magnetic field is mu naught I over 2 pi r. Alright, so now I want to treat the area in between B and C, and so I've drawn a cross-sectional shape here. The first thing we're going to want to figure out is how much current is actually enclosed. Well, let's find out just the current being enclosed by this first of all. In order to do so, we need to find the area of this shape. Now I've drawn it here as a bird's eye view, and if you want to figure out the area of this shape, this is like a hole. So all I need to do is take the area of the larger circle and subtract the area of the smaller circle. And since they're circles, it says pi c squared or pi b squared. So this comes out nicely, pi c squared minus b squared. Now, that's the area. However, now I need to consider this j enclosed. J enclosed is going to equal the j that's already being attributed from the central wire. So I'm just going to call that a plus j. And keep in mind these are vectors. And then we have this partial j. Don't really have a good way of representing it, but the important part is that it is inside. So I'm going to call this a minus, and since it's a partial j, let's just denote it as a small lowercase j. Now this j is what we're going to have to really tackle. If I rewrite this in this integral, I get mu naught over 2 pi r integral j dot dA minus integral lowercase j, because it's not all of the j, lowercase j dot dA. Now this integral is corresponding to this piece right here. So we've actually tackled that before. That's just mu naught I, 2 pi r. So our entire rest of the calculation just depends on evaluating this integral right here. Now, this partial j, which I'm going to rewrite here first of all, integral. This partial j is going to be the total current that's going in I divided by the total area, which we found here, pi c squared minus b squared. And this differential area element we just leave as dA. All of these terms here are constants, so I'll pull those out. But now I have to integrate the area. Now what does the area start from? Well, the area element is going to start specifically from B, because it doesn't start from 0, it starts from B. That's the region we're considering. So the area at B, well, that's just a circle, pi b squared, all the way to the area of our Amperian loop, which again is a distance r away. So pi r squared dA. And this simplifies to I times pi r squared minus pi b squared divided by pi c squared minus b squared. These terms cancel, and I'm left with I times r squared minus b squared c squared minus b squared. So now all we need to do is plug this in here, and that's going to give us mu naught 2 pi r. I'll factor out an I. We get a 1 minus. So we have all this term, r squared minus b squared over c squared minus b squared. But we can simplify this by rewriting this 1 as c squared minus b squared. This and this are going to cancel because one's minus, one's going to plus, and our final answer for the magnetic field, and it's the form that I would keep it in, is c squared minus r squared over c squared minus b squared. So, down to the last one. All of these, this one turned to be really an exhaustive process, but this one, as I claimed, would be the easiest. And we can see that because all we need to do is consider J enclosed. Well, if I look at J enclosed, we have to look at our Amperian loop. But this one is going to be way out here. And which currents are enclosed? Well, you have the positive J coming out and the negative J coming in. Both are of equal magnitude. So we get J minus J, which is 0, which therefore implies that B in this region is 0.